Hi, welcome guys to another episode of Ground Control to Major Nerds. My name is Shrikant Chitiala, and I'm an avionics systems engineer and a system architect. Today, we're coming in with a really tragic incident that occurred on June 12th with AI 171, the Air India flight AI 171 from Ahmedabad to London Gatwick. The aircraft took off, and within 32 seconds of its flight, had a tragic accident where all 242 members on board were presumed killed, with one survivor now uh, reported in the hospital. Our thoughts and prayers go to the families that are dealing with this incident, and our condolences to the families and to the affected people, not only in the aircraft but on the ground as well. The death toll as of now reported is 290. Again, this is a presumed record. It is not factual yet. We are still uncovering more details as the investigation goes on. Another point to actually bring to attention of the listeners is all the speculations and theories that are going out are just speculations and theories. Myself being in this industry for over a decade now, and also having the aviation background that I have, cannot rule out anything to say this is the reason why this accident happened. And it requires a deep understanding through the investigations, which are led by the Indian agencies, the Air India authorities, the DGCA, the AAIB, which is the Aircraft Accident Investigation Board, and also the Boeing regulatory authorities, along with the NTSB on their side. There's a lot of investigation happening. There's a lot of fact checking happening. There's a lot of data that's coming through. They just recovered the black box, the FDRs and the CBRs, which is the flight data recorders and the cockpit voice recorders. Everything is getting analyzed at the very, very minute level to understand what is the real reason why this incident happened. So I would not, in this episode at least, speculate or even give my opinions on what would have caused this incident. And I would wait for the thorough report to come out before we can dive into it in a separate episode for this. Having said that, our topic today is aviation safety. We will be diving into what actually happens to attain these aviation standards when we fly, to make the aviation standards met and aviation safety adhered to. We're gonna we're gonna discuss different topics, different level of expectations for flying and for developing such complex machinery to fly. So, having said that, I would like to introduce my constant co-hosts, Ashwini and Parvesh. Ashwini, how are you
Yeah,
doing?
hi everyone. Obviously, I'm in a somber mood right now. Um, our hearts go out to the families of everyone who've lost their lives, everyone who's been affected by this incident, and obviously, as uh, people in the aerospace community, this has hit us hard, not just professionally but also personally. And I remember being at Delhi airport when I heard about this. I was flying down to Mumbai, and I could sense the mood in the air with how passengers received this news and how there was a little bit of fear and trepidation on stepping into an aircraft. But it is important to remember that statistically, airplane travel is still one of the safest ways to travel. And there is an entire system of safety, which is what we will be discussing today. And we are here not to speculate, like you rightly said, but we are here to ask about what is this aviation and aerospace security and safety mechanism that prevents incidents like these. Why airplanes falling out of the sky is an extremely rare event, and when this does happen, why we are all shaken up, and how do crashes like this reshape our entire approach to aviation and aerospace security and safety. So I believe that is a good discussion to have right now rather than speculating on what may have caused this incident. Let us all just wait for the reports from the authorities and then let's get to that.
Okay. Yeah, thank you. I just also want to make sure that I mention this, that is it is a dark day in Indian aviation today. Not only Indian aviation but the world aviation. These incidents don't happen often, and it should not happen often. It shall not happen often, because that's what we, as aviation engineers, or aerospace engineers, aeronautical engineers, do every day to make sure these incidents don't happen. And when these happen, as Ashwini pointed out, it reshapes the whole mentality of how we design systems, how we design aircrafts, and this will definitely teach us a lot, the whole incident itself. But yes, the cost every time this incident like this happens is very huge, and that's why we are very careful about how we talk about it and how we learn from this as well. So, with that, I would like to also introduce Parvesh. Parvesh,
Hi,
how are
this
you
is
doing?
Parvesh. I'm good. I am in a sort of off mode because it is in a big tragedy. I'd just like to reiterate what my co-host said. It's not a time for speculation. It's a time to show empathy, sympathy for the families involved. Um, do what you can for the families, thoughts, prayers, whatever you can. And yeah, that's all I have.
So, with that said, let's dive into this topic of aviation safety. Where do you guys want to start? So, I think we all come from different backgrounds. Parvesh comes from the propulsion side, from MRO side, and from also the business analytics side. Ashwini, you come from the R&D side, specifically with the R&D in drones and in defense developments, as well as you have experience in aviation R&D as well through your academics and after the academics as well. And I completely come from only aviation part 25 side. So we'll be bringing that to the table today. But where do you guys want to start off? Like, what do you think?
Start with safety and design, maybe.
The safety and design. Okay, let's start with that. Um, I guess it's a good time to ask this question. So, how does aviation safety even come in play? Like, where do you think is aviation safety? Like, safety, I think, is there in every single design that any engineer does, right, regardless of aviation or not. Why is it so special in aviation that aviation safety is considered to be the gold standard than any other engineering design?
So, if I can just start off by exactly answering your question, uh, as common people, we usually think that safety is something that kicks in when something flies or during flight. But for us in aerospace R&D, safety starts long before something has taken off for the first time. It starts off way before that, when we first start planning to design something, when we first decide to indulge in a project that is eventually going to fly. The first thing we think about is whether this is safe enough to do. The first thing that we do is something called hazard identification and risk analysis. So we essentially look at making this piece of technology. But before we do that, we identify what could be the hazards while using this technology. Using those analyses, we come down to system requirements, which is, I'm sure, something that you can spread more light on. But these system requirements typically dictate safe and proper usage of any technology that is going to eventually be airborne. And why aviation and aerospace security and safety is considered the highest level of safety is, I will give you a very layman example of what one of my professors told me. If you're learning how to drive a car, something goes wrong, you push the brake, the car comes to a stop, you are safe. Once you're airborne, if something goes wrong and you decide to switch off systems, you are still in an inherent unsafe space, because your airborne system is essentially being converted into a projectile which can crash, not only killing you on board and all of the passengers on board, but also creating massive havoc and damage on whatever it has crashed upon. So once you're airborne, you do not have the luxury of just stopping everything, right? So it is very important that you consider the safety and security way before something is airborne, way before you have started doing any sort of designing, any sort of testing. Just during the conceptualizing phase, it is very important to come from a factor of safety.
Parvesh, any thoughts on the same?
Just the same. I believe as engineers, right, we usually have like a order of magnitude factor of safety. It's not like, oh, let's just like multiply it by 2. It's like, let's multiply it by 10. That's what it usually is. But we can go into all of that stuff further.
All right. I guess let's break down how aviation safety actually works in terms of design then, right? So um, from my experience, I think systems engineering is where the aviation safety aspects start. And the biggest question I think in any engineering, or at least in aviation or aerospace, is what is systems engineering, right? And systems engineering is the engineering aspects where you plan to design a system from start to end by validating and verifying and having a structure to those validations and verifications. The systems engineers sit at a 10,000 feet and looking at the big picture of the whole design. And that's where aviation safety methodologies also come in when you're trying to do a design goal, basically, to achieve that goal. So,
Is there any specific methodologies, like standards for that?
yes, systems engineering in itself is like a different engineering branch, I would say. And the methodologies that are used depends upon what you're trying to design. Like, for example, if you're trying to design fail-safe systems like the aircraft, then there are recommended practices that you have to use to make sure those design goals are achieved. And some of them are the ARPs, which are called the Aerospace Recommended Practices. And there's ARP 4754, which is now B, which is gone to Rev B. And there is ARP 4761, which is now to Rev A, so 4761A. And these together make up the ideology of how aerospace designs are achieved. They are a huge recommended practices guidebooks, which enable you to make sure best practices are achieved while you're trying to write your requirements for your aircraft systems or your aircraft in itself as a whole integrated system, or you're designing certain systems that are heavily dependent on aviation safety. So,
Do you have anything like, okay, like any specific practices you know from it? Like, just give us an example, we don't, just for the
there is
audience.
so the whole thing is actually like a practice in itself. Like, there is no specific practices that actually combine to be like, okay, this is one aspect of ARP as a whole is a practice in itself. One of the biggest things I think in systems engineering is basically like systems engineering. If I could refocus on that topic, it's basically an interdisciplinary field, right? Which is focusing on design, integration, and management of the whole complex system throughout its life cycle. So that's why when I said that systems engineering engineers sit at a 10,000 feet looking at the big picture, that's what it is. So that's why systems engineers and safety engineers go hand in hand for that reason. And that's why there is a lot of influence of systems engineer and aviation safety. And they also try to imbibe a lot of validation and verification as a methodology to make sure that the systems are safe and they are designed to the requirements that are set by the stakeholders, and design, and also they help to shape the requirements as well on how the system should be operated. So that is what in layman terms it is. So
If I
yeah.
can just jump in here and I'll just add to a few things that Shri has said. Uh, as someone who works in the drone R&D and production field, I will say this. A lot of our safety systems, a lot of our quality standards have been derived from aviation, from what we've seen over the last 50 years, guiding what aviation safety is for airplanes in the sky. And there are a lot of very important standards. There are a lot of very important certifications that we follow during R&D for any drone system. And one important aspect for this is when we sit down and start developing a new product, we make something that is a mission risk matrix, where we define what risk is, we define what the different levels of risk is, and then we define what an acceptable risk is. Uh, And this depends completely on the application that our technology is going to be used at. If this is a military drone, if this is a civilian drone, or if this is something which is going to fly within visual line of sight or beyond visual line of sight, whether this is manually being flown or whether this is being flown autonomously. There are a lot of factors that ultimately decide what the final application of this product is going to be. And based on that application, there are a lot of quality and safety parameters that we consider. One important parameter is the certification. What sort of quality standard, what sort of safety standard are we adhering to while we make this technology? For example, we have MIL standards when we are making something for military applications. We have STANAG standards, which are international standards followed by regulatory authorities for certifying such products. We have environment protection standards, such as JSS Pentafile. So these are all critical for safety. It is very critical for compliance, and it is very important that these safeties are uh, added to our design phase before such a product is developed. One of the things a mentor used to tell me regularly was that if you do not bake safety into your mission profile at the design level, you will be duct taping it on later once the product has been developed. And duct taping on something after the product is developed never ends well. So it is very important that you start from a factor of safety, and that is what will help you make a product that is not only usable but also safe. And purely from being in the field, I can tell you this: as people in R&D, we are eternal optimists. When we design something, our we are in the sky. We feel that our technology is going to always work. We are always very optimistic that anything that we design will fly, it will do well. But we have to be shown where it can be failed, where any technology can fail. So there is an entire department in a company called the safety department, which is full of pessimistic people. And we, as people in R&D, always butt heads with them, where we say, why do you look at our system so pessimistically? Why do you always say this will fail here, this will fail there? But it is so important to have them in place, because they see the picture that you were talking about, the larger picture. Our system is not only going to be used in a lab setup in ideal conditions, it is going to be used in the real world, where the temperatures fluctuate, where the wind conditions fluctuate, where environment is not usually conducive to having a very safe flight envelope. These are all factors that exist. So the safety department, the quality department, these guys, they are able to foresee these conditions and then impress upon us not only a factor of safety that is for the entire technology that is going to be airborne, but every system and subsystem also. So we are not only checking uh, as an entire structure, an airplane or a drone is able to be airborne, but every single subsystem, like the landing gear, like the sensors, like the wing assembly, like the camera that's your payload, all of these things have to be safe individually, and then collectively put together, they should add to the safety of the product.
And Sri, can you I'm sure you also dealt with a lot of safety related issues, right? So I know Ashwini told us about how it is in drone manufacturing. Can you sort of translate this over to aircraft manufacturing for us?
Yeah, sure. I think the part 25 is where I think the commercial aviation regulations according to FAA standards fall, right? We do not just rely on somebody to be pessimistic, taking Ashwini's words, to be honest with you. We Because that is something, again, human factors is a big deal. We do not want to just rely on some people, hoping that some people actually like are pessimistic and are looking through that. We rather follow a very structured approach when it comes to commercial flight. uh, Believe it or not, I think there is more safety baked into commercial aircraft development than even defense. Reason being, I think
Yeah,
the
there has
defense
to, right?
requirements. Sorry.
There has to, right? Because it's a lot more lives
Yes.
on stake.
Yes, but if I have to give like the analogy, right, people assume that the defense would be more rigorous in their R&D, and maybe because of the things that they do, they might be more um, exciting in their design approaches and the way they build products. But I have to let you know that that is not the case in commercial aircraft manufacturing or aircraft design. It is much more rigorous, much more detail oriented, and much more investigative than the defense as well, for the sole reason of making sure incidents that we just witnessed does not happen. So to start off, aviation, like the aircraft manufacturing world, it starts off from the requirement writing from the stakeholders, right? So that requirement writing follows the ARP standards, and ARP has been something which has been out there for like 15 years now, but it comes from the space world where NASA famously said failure is not an option. And with that ideology in mind, the ARP standards also have been derived from, where each and every corner of requirement writing on why is this requirement even required, right? Why are we writing these requirements? From that approach, those practices have been put together and the checklists have been put together for every single level of detail of what you're trying to design. So, starting off from there, requirement writing, we as systems engineers sit together at a high level, understanding the mission of this aircraft that we're trying to manufacture, going from the top level requirements, marketing requirements, financial requirements as well. Also, mission scope, what is the actual mission of this aircraft that we're trying to design? At that level, we start off, and then it goes from that level top down to the lower level requirements until we come to a point where we are at a subsystem level requirements, as we say, where we go from the requirement writing for systems engineers per the ARP 4754B practices. Like they go from the top level requirement writing with the stakeholder requirements inside, and then we cover not only just the stakeholder requirements, but we go through the stakeholder, financial, marketing requirements, mission requirements, and what exactly are we trying to make this aircraft fly for. Basically, those requirements are written at a top level. Then we go down the list to the technical requirements, the functional requirements, the subsystem requirements. And that's when I think the requirements for the software, the hardware, the different disciplines start off. So once we, as systems engineers, like have understood what the aircraft requirements should be and what should be the goals of the design goals of this aircraft should be, that's when I think we go down the list and we start doing the subsystem and the component level requirements down the line.
How
So
big is one of these requirement documents
so
on average?
basically the the requirement writing documents could be a lot, like just the top level requirements could be 1000 to 2000 objects basically, so that would be around maybe 100, 200 to 400 pages.
It's like a novel level size.
Yeah. So one thing is for sure, system engineers have to write a lot of requirements, and it could be like the English in itself, the literature itself is pretty long. So yeah.
Do you like jot down the requirements in terms of notes, like how you'd really take notes, or is it more like you have to be very specific with each, even your wording, like
There is a whole
does it have to
requirement
be?
writing standards. So ARP gives you those standards. So we use a lot of shall statements to make sure that
Okay.
the shall statements are definitely supposed to be adhered to. And then we if we are not using shall, then they are not requirements, they are just rationales, or they are just like commentaries on the design goals itself. So there's a whole set of requirement writing style that systems engineers use to write requirements. So there is a whole structure to the madness basically. So whatever is produced in English, it's not just verbs, the verbages and like writings only, like notes. They are basically tools that we use. There are different kinds of tools, like IBM has got a doors tool which helps you structure these from top level to the lower level requirements. And there is something called traceability. Like imagine, like, to give you a scenario, like if we want to design a parachute, for example. I'm not going towards the aircraft because it will be too obvious, but let's say you're designing a parachute for two people to use it, right? So you start off with okay, the requirement is that it should bear the weight of two people, right? And then you go down, okay, what kind of, flight profile do you need for those passengers to come down? Did you want those two people using the parachute to fall down at a very fast rate, or do you want them to have a very smooth, like, uh, deceleration? So depending upon that, then you start designing the parachute cloth itself, like, and then do you want it to be lower, like a lesser weight of a bag, like in which that you're trying to put that parachute in, or do you want to just have that parachute to be big, and once you're jumping it just deploys automatically behind you? So those kind of things you start like writing up, and then you start going down and down and down, and depending upon how your mission scope and how your product scope looks like, and your design goal looks like, you start envisioning things at the lower level to then trace up to the higher level requirement, which is, okay, if you want this parachute to be fitting in a bag of 20 by 20 by 4 basically dimension bag, then you got to now make sure that your materials are thin enough and at the same time robust enough to handle two people's weights, right? So you got to trace up to the higher level requirement from the lower level requirement to make sure that you're validating your design goals at the end. So there's a whole structure to this madness where that's when the ARP comes in, even at the aircraft level. So just to give you an aircraft example, like for example, the fuel system, right? So we had an issue with one of our fuel systems where sloshing was a big deal. We were not able to make sure that the center of gravity could be, arrested at a
Uniform.
certain, rate, like the burn rate of the fuel along with the bank angle of the aircraft, the fuel sloshing was happening. So we were not able to get the right measure of the fuel tank of what levels the fuels are at, right? So we had to then go back to the drawing board while the aircraft was already in its experimental flight phase, try to make sure that we make structural changes to the wing box to have better fuel slosh calculations, and at the same time add additional sensors to make sure we have clear indication of what the fuel levels are on each wing box basically. So things like that. So you go back and forth only because you have that structure, only because you have that traceability at different levels. So you write down from the top to the bottom, but then you trace back each of the requirements from top to the bottom. So that's how it is done. So there's a lot of techniques involved in it. There's a lot of practices that are involved in this, and all of them are part of the ARP and the systems engineering, we call it toolkits, which each and every company has its own way. Some of them use the V diagram, which is basically validation on the right, sorry, validation on the left, verification on the right. Basically, you keep going into into a finite loop of every single level of requirement writing that you do. You try to validate it, saying, okay, do we need this requirement to be met? And once you have validated the yes, we need this requirement to be met, then how do we meet those requirements? You verify it. And during the verification phase, if you realize that, okay, we are verifying that this is getting met, but at the same time the end design goal is not getting met, then we go back again to requirement writing and make sure that we change those requirements back again so that we can validate it correctly. And then this cycle continues until we get to the top level where the top requirements are getting met with the top verifications too. So we can deep dive this into a different episode where we can go and we can give examples. We can do a working session also with you guys to see how does the systems engineering aspect actually works. But yeah.
So it's sort of like you build a step
Mhm,
and then you go back down and then
mhm.
climb back up and see, okay, the step is aligned, then build the next step,
Yes.
come back down, go back
Mhm.
up.
That's a good
Okay.
analogy, actually. Yes. So, and while you're doing these steps, you try to make sure that regulatory requirements are met and safety requirements are met. And robustness is also baked in at each step. So, when you say things like the aircraft shall fly at 65,000 feet, you make sure that the aircraft structures safety requirements are written, aircraft engine safety requirements are written, aircraft performance safety requirements are written, so that the aircraft shall definitely fly at 6,000 feet, but also for robustness sake, we'll do plus minus 10% of it, right? Of the requirement. So we will add like 6,500 feet more to it so that it can definitely perform at 65,000 feet. So that's what Ashwini was trying to say before. So we try to make sure that we overcompensate for those requirements when we're trying to verify the requirement itself. So that's the safety and the robustness that we build in to that design. So
Okay, so another thing is, let's say at the testing phase, right?
Mhm,
Obviously, you don't fly the plane immediately to test it. There's wind tunnel testing, and there's a bunch of other testing you do.
mhm.
Give us like a sort of taste of what
Okay.
kind of testings there are.
Yeah. So at the top level, there is no specific tests that we can do because at the end of the day, at the top level requirements, like you have to do your experimental
You have to
flight
fly
tests
it,
to
yeah.
prove that your mission scope is met, your stakeholder requirements are met, and
I
ultimately
understand that, but like
all
what
those.
safety measures are taken for during that test?
There is enormous safety measures. Like basically every single test that you do, at least from my experience and from the civil aviation world, even if it's an experimental flight, right, you have to make sure you're having a solid config management plan, and your config management plan involves different kind of labels. That's what we call to the test artifacts. Basically there's a blue label for prototyping, there is a red label which is for experimental flight, and there's a black label which is production equivalent flight, right? So throughout these labelings of the boxes of the aviation, the aircraft systems, we make sure that rigorous testing is done, and we make sure that before it's put on a flight test article, it has passed through FAA regulations to make sure that its safety is adhered to. At the end of the day, it's still an experimental flight test. There's still risk involved when you're flying an experimental flight, but the lab testing and the qual testing that's been done on the individual system itself, and multiple of them when they're put into a into a flight test article, they have gone through rigorous config management checks to make sure that they are safe to fly. So a lot of safety is considered even at the flight test, even at the experimental stage. So that is what is done at that stage. Now, coming to the lower level testing, even at the lab level, there is a heavy config control that happens in the labs and that happens in the development phases as well. So, for example, there are DOs, which is directive orders from the FAA. So there are different DOs for different kind of developments that we do. So, for example, if we are making a radio, a transponder, right? For example, the transponder has its own regulatory authorities, regulatory standards that we have to meet. One of them being the DO 181F, which is the current standard. So the DOs tell us what are the requirements what are the minimum requirements, which we call the minimum operational procedures or MOPS. What are the minimum requirements that the transponder should be doing or shall be doing when it's operating in a Part 25 aircraft? So
Okay, so one question here, is there a difference between DOs and airworthiness directives, or are they both the same thing?
there is a difference. So airworthiness directives are basically, those are ADs, and those come at a higher level than a just like a functionality level. So DOs are usually uh, for a specific discipline like transponders. That's a discipline. DO 178, which is basically for software substantiations and software certifications, right? So that's a different discipline. So, but airworthiness directives, I think they come at a higher level than that, like at an integrated level. So hence it's at a different stage of certification slash adherence to development, basically. So that's where it comes to. But coming back to the topic of you know uh, getting things validated and verified, the DOs are the biggest things that guide civil aviation to produce products to a certain standard which would be safe to fly, and also adhering to the airworthiness side of things for the civil aviation. So depending upon which discipline you are in, there are multiple DOs that you have to adhere to, and depending upon what safety critical system you're making, the DOs get progressively more rigorous. So Again, I'm just scratching the surface. We can do more deep dive episodes on certain disciplines and certain DOs if required. If there is an interest, please comment below, and we can talk about those specific topics. So yeah.
So coming back to Ashwini, um, Srikanth has told us like a lot about the safety that we've done, right? Does drones also have this level, or is it like less? Is it more? Like, what is the level of um, safety that is taken into account there?
I think as a relatively newer technology, like I previously mentioned, a lot of our safety standards are derived from aviation. We have been looking at the aviation industry that has existed for the last 100 years, and we have learned from a lot of their mistakes, and uh, we have borrowed, and we have sort of not, I wouldn't say edited, but borrowed and then heavily used a lot of safety standards that already exist with commercial aviation and with defense related standards as well. One aspect that Srikanth uh, mentioned, I can sort of give you a slightly more detail about, is when we look at production. We've already covered what design phase is like. From design phase, you're making something into a product. So you're going into production phase. When it comes to that, we rely on vendors who are already certified. What does that mean? What it means is we are looking at people to give us raw material. That raw material has already been tested and has already been standardized and has already been certified. For example, if you're making the body of a drone, and it has to be made from metal. Traditionally, we are going to be using aluminum, or we're going to be using titanium. Why? Because these are the materials which are light enough, but also at the same time give you enough structural strength. There are traditional uh, sort of alloys of aluminum, of titanium, which with very specific chemical properties that have been certified for use in aviation and aerospace, for use in drone manufacturing. These standards have already been set. How? Through previous experimentation on materials themselves. Material experts will know that there are tests such as Izod-Charpey test, which test where the fracture happens. There are tension tests, there are compression tests, there are stress tests. These are all materials that go through these tests, and then they are standardized. So that standardization is then applied to a vendor, and the vendor is giving you a certificate along with the raw material that this material has been tested, it has been certified for use in aviation and aerospace. So that is how safety is baked in while production, right? Similarly, there is safety when it comes to, say, coding. There is cybersecurity. You have to ensure that any software that is on board for any drone cannot be hacked. It is encrypted so that people with nefarious intent cannot hack into your drone and ask it to do rogue missions, right? So that there is an aspect of cybersecurity there. There is a concept of coding where you have to ensure that your software runs for an X number of hours before you can say that this software is good enough to be put on board of an autonomously operated drone. Similarly, if there is any mechanical component which has to open or close, for example, in a payload delivery drone, typically you will have a trapdoor that opens and then a payload is dropped. That trapdoor has to be certified and rated uh, during our writing of our mission requirements. We have to ensure that this trapdoor op- is capable of opening and closing 50,000 times over the entire operation of the drone as a product. So that trapdoor, after being manufactured for the first time, is sent to a lab where it is opened and closed 50,000 times. And you ensure that the life of that component exists. All of the
Wait, but
linkages,
if
all
you open and close it 50,000 times, you run out of life, right?
exactly. So when testing happens, one unit is made and it is stress tested. It is completely tested as if it's going through its entire life. And we observe whether our written directives are met. If a landing gear is able, it should be lasting 500 cycles where it has taken off and landed 500 times. That test is actually done physically to ensure that that life exists. Only then is the part then pushed on to an actual product. In a
To
lot
answer
of
your
cases now,
to answer your question, Parvesh, that's the test article that Ashwini is talking about. It's not the actual
Yeah, so it's like
artifact every single time that it's gonna be used. So it's the test articles that are
right?
subjected to that level of stress, and then they are validated and verified to be like, okay, this will be in operation in the field. It will be doing this level of operations, basically.
yeah, so basically you make like a batch and then you pull one part out of the batch and
Correct.
run that one. Yeah.
In the last 5 to 10 years, thanks to software development, a lot of these tests can also be done through simulation and through analysis. So there's a lot of simulation testing that also is allowed for certification, but then a lot of critical components are pushed through actual testing, and then they are pushed into actual production. Now, once the system is made, your entire assembly is done. Then again, you go through very rigorous testing to ensure that your product is not failing as a whole. Like I said, you must have safety through all components and subcomponents, through all assemblies and sub-assemblies, and then all of them should come together and also be safe. You should add to safety. It should be an additive feature, right? So that is how you ensure that safety exists. Now, one very important thing we should understand is safety does not end once your product has gone into service. Safety is a continuously evolving subject. So every mission that happens, every time your technology is airborne, you are continuously monitoring every system, every subsystem, and you're gaining data, you're gaining knowledge. And that is when you decide that these are the features that we predicted would happen, this is how it has happened, and now these are the few additional steps you can take to ensure that the next version of the product is even safer. If I can give you a very layman example of this, if you watch the Iron Man movies throughout the entire existence of this character, you will notice that he started off with one suit in the first Iron Man movie. He went through a few iterations. Every time there was a significant event in this person's life. For example, I think his friend, his character called War Machine, was airborne. His system crashed, and then he crashed. He learned that his system should have a parachute inside the Iron Man suit. So the next time you see another character, the Spider Man's Iron Man suit is also airborne. His systems fail and he's starting to crash. There is a parachute in the system. So this is the this is a very real life example of how safety is baked into the system. We continuously monitor systems while they are in operation, and we see it does not have to be a critical failure. We are not waiting for a crash to happen. Just a slight deviation from the norm is something that was detected, and we then push into it a new upgrade through which the product is safer. So it's a continuously evolving cycle of making products safer.
Okay, over here, I would like to step in and also say whatever Ashwini spoke about, the civil aviation world and the development of systems in the civil aviation are much similar to that, at the same time even more robust than that. So
Yeah.
the design phase may bake in safety requirements and safety regulations, and while the design goals are getting established, but at the same time I think the whole process goes from what we call uh, cradle to grave, right? So we look at the entire life cycle of it, and it's not just the aircraft and the aircraft systems itself, but also the operability, maintainability, reliability side of things too. And that's actually a big part of systems engineering work and safety engineering work, where the LATs that we call the availability, maintainability, reliability, operability. These are the four things that are like heavily written down. Like any kind of procedure that you observe that the maintenance crew do, or the pilots do in terms of checklists, or the standard operating procedures, everything is written to the dot by the systems engineers and by the engineers who are helping the systems engineer to write them, like the expertise in those fields, basically the propulsion guys or the mechanical guys or the hydraulic guys. Like we take help from them to understand the effectiveness of their systems and then bring it up to the level where the operability could be met, right? So aviation safety doesn't just end at making the product itself, but also continues throughout the life cycle into the maintenance side of things, into the operational side of things, into the availability side of things, where like, do we know, okay, after a flight, how long can it actually recover from its stresses that has been put through and then again be available to fly, right? So those also have been heavily researched, heavily tested, and then a standard operations manual has been set up for it for to continue its operations. And also its predictable failure has been already analyzed and already understood and written down to make sure that x number of hours of its operation will lead to a failure. That's been written up. And to avoid or mitigate those failures, what could be done or what should be done in terms of maintenance has also been written up. So tying back to the incident that has happened, the reason why there is a shock in the aviation world for this incident is the same reason. This aircraft has flown for about 16 years. We know what its predictable failure rate is, and since it has achieved its failure earlier than its time, the reasons for it will actually enhance the whole design of the aircraft again, and its operational manuals again to be written up so that this incident or this failure would never happen again. So that level of detail is taken into consideration while aviation systems or aviation uh, subsystems are developed. So yeah, I just wanted to highlight that.
There's two more things I want to hear your guys' thoughts on
Mhm.
before I move into the financial aspect of this. One is redundancies in aircraft systems, and second is life limited parts. So, who wants to take?
Ashwini, you want to start off with something, or I can dive into both? Okay, so redundancy for me, I think
Wait, start with life limited parts first. Let's go to
okay,
redundancy after that.
life limited parts is something which is not in a designer's control, right? Like you design the aircraft, you design the subsystems to your requirements and your design goals, and then you pick the components that could fit your requirements and that could achieve your design goals. And by the time you certify the aircraft and you fly it, maybe within a year or two, you'll have an obsolete part, right? So that obsolescence is something which is not in the control of the designer. We would try our best to make sure that obsolescence is avoided, but it is never a certainty that obsolescence could not be avoided. So I guess that's where the requirement writing part becomes critical, where we write requirements in such a way that we are not limited to certain components in itself, whereas we are more flexible to change of components and to change of uh, you know change of designs basically if required to meet that requirements. So I would say like obsolescence is a part of maintainability and operability of aircraft systems, and we work through it, and we work through it until the end of life of the product. So
After the life that is calculated,
mhm,
the possibility for failure increases, right? So that's why we have life limited parts, or is
yeah,
there like a different reason?
um there there are there are two reasons, right? One is the MTBF, is what we call mean time between failure, right?
Yeah.
So which is actually calculated using the systems engineering analytics, like the ARP 4761 defines what is an MTBF should be, and or MTBUR, which we call mean time between like unit replacement, or like mean time between failure. Let's stick to that, right? For example, so those things are calculated for a component when it is selected, and through rigorous testings there has to be a number that needs to be achieved depending upon how critical your system is. Like for example, a microcontroller on a flight control system, which is a FDAL A plus system, right, which is catastrophic. So a catastrophic system like flight controls, having a microcontroller will be having a very high MTBF, meaning its failure rate has to be very, very low. Whereas the same microcontroller being used in a SATCOM, which is an FDAL-D, which is just a minor system, if it fails, it fails, right? We don't have communication, but the aircraft still flies. So depending upon where you're using those components, its MTBF requirements change and its failure rates acceptability of its failure rate changes, right? So the other reason of like a life limited unit or a component would be the manufacturing rate and the manufacturer itself, which is out of bounds for designers. Basically, if the business unit goes bust, we cannot change that. Or if the business unit that makes these components decides that they don't want to invest their money in manufacturing these components, we can't do anything about it. So the only way we can avoid it is if we know that we have a product line which is dying in 20 years, we just do a lifetime buy for those components so that they have to then produce X amount of components to sustain the 20-year life cycle of the product. So
So it's sort of like spares.
yeah, spares and also manufacturing lines. So uh, I can tell you from my space of work, working on transponders, we do lifetime buy because we know that our transponders are gonna see the end of life in 10 years, right? So for 10 years, we have a predictable number of spares that we can order, at the same time number of units that we're going to deliver to our customers, we know. So we just do a lifetime buy for that X amount of components that we need. So yeah. Now,
If I can
Redundancies?
just give
Mhm.
you
Oh,
my
okay.
2 cents on redundancy, um, it for me, redundancy is essentially the crux of aerospace safety. And you can think of redundancy as the safety net under the safety net under the safety net, right? And in aerospace, when failure can mean loss of life, and redundant, it means there can be a lot of loss, right? Redundancy is how we protect against the unexpected. Uh, it is protection against the this should never happen, but it might happen. That sort of moment. And for me, redundancy means we are deliberately designing multiple ways for a system to keep working. Even if one part fails, then there is still uh, the capability for something to work. It is not enough for us that a system is working when everything is perfect. It also has to keep working when something will inevitably break, because failure will happen. It is incredibly critical to have redundancy in your system, because every component, like Shrikant rightly said, it has a mean time between failure, right? No matter how reliable a component is. So there are a lot of factors uh, which accelerate degradation of any component. And eventually, in your missions, because you're flying, because your system is working in an environment which is not conducive, ultimately, there is going to be something that will eventually break. So that is why you must have redundancy in place. It is like driving while wearing a seatbelt and also having airbags, because you never get to choose what sort of an accident you will be in. So it is important to have the seatbelt. It is also important to have the airbag, right? And we have to understand that human lives are at stake, and expensive hardware is at stake. Years of research is at stake. So it is very important that failure cannot happen. So you have to ensure that redundancies are in place. There is something called a single point of failure, called an SPOF. It is very important that if there is a system that has no redundancy, just a single point of failure can mean that our entire system has fallen down. So there is a very old saying: for the loss of a horseshoe, an entire battle was lost. We cannot have that in aviation. So avoiding single points of failures is one of the most critical reasons why redundancies are in place. For example, in a drone system, we rely on global positioning system, or GPS, to ensure the accurate positioning of a drone so that we can give it accurate autonomous waypoints to fly. It is a very realistic scenario that these days jammers exist that jam and spoof the GPS location of a drone. So redundancies have to be in place so that in case jamming or spoofing of drones happen, there is still a reliable fallback for the drone to accurately navigate in the sky, even if GPS does not exist. Right? That is a redundancy. So a single point failure of lack of GPS cannot mean that your drone has now crashed. So that is what I mean by SPOF. And ultimately, all aerospace systems are interconnected. Everything is being fed into a flight computer, which is taking decisions. It is a feedback loop of sensors and of flight computer directives. So if one point fails, that can cascade into an entire system failing. This is why redundancies should exist. So these redundancies buffer these interactions and they give you time to respond and time to react. And it is not just about having backups, it is about giving the system time to catch its breath and catch that error and not allow it to cascade into building failures. So that is just my 2 bit on redundancies.
Yeah, Ashwini put together why redundancy is required. I would say that how redundancies are done, basically. It is a whole different ball game on how redundancies are designed within systems. And again, ARP 4761 guides us to know what kind of redundancies are required depending upon your FDAL, which is basically your functional design assurance levels, right? So if your system is a catastrophic system, then you better have enormous amount of redundancies to show critical functionalities are not falling on single point of failure paths, right? And if your system is down the line a minor system, then I guess it is good to have redundancy, but it is not a required aspect depending upon you know its its operational environment basically. So for example, in cabin Wi-Fi, sure, if you don't have a Wi-Fi, the customers might be pissed and your business might have a hit on it because you're not giving good customer service, but it's not safety critical. So again, requirement writing plays a big role when you're writing your stakeholder requirements, your market requirements. Systems engineers have to be very empathetic to the business side as well. Hence, these design assurance levels are written up so that the business or the safety side don't go one way or the other heavy, right? So there's a fine balance where requirements are written to make sure that systems that don't require redundancy maybe will not have redundancy for its own reasons, but systems that definitely should be having multiple layers of redundancy so that single points of failures don't exist in any way possible. Yeah, the recommended practices will tell you and shall tell you to do them. And if you don't have them, you better have a very good reason why you think your system is so reliable that you don't need redundancy. And we can go down this rabbit hole in another episode for sure, because there's a lot of techniques that are used on how redundant systems are built and developed and what goes into its development cycles.
We can even talk about like interesting redundant systems
Yeah,
in that
definitely.
episode.
Like, yeah, your your area of expertise, propulsion. I think FADEC is one of the most complicated systems on the aircraft. With, I think I can't even remember how many test points we had for our FADEC system on Gulfstream. I think it was like the test procedure itself was 2 to 3 weeks long, performed by a person who knows how to do it. Basically, if you're new to it, it'll take maybe 2 or 3 months to perform that whole test. So that's the level of detail that goes into like very critical systems. So yeah.
So from here, I kind of want to pivot to importance of safety from a financial perspective, because as a
Mhm.
business analyst, this is somewhere I'm a little more interested in. So do you guys have any other thoughts to
No, actually,
before I go in?
while I was talking about the redundancy side of things, I was telling you the fine balance that's required. So when we're writing requirements at a stakeholder level, right, we're talking about
Yeah.
market requirements, financial requirements, at the same time the stakeholder requirements for the mission of the aircraft slash the system that we're designing. So I think that's where I think you can come in and tell us, as a business analyst, analytics role that you have, how does uh, you know, financial decision making impact safety in aviation. So, yeah.
So basically, one thing is we know that there's thousands, hundreds of thousands of commercial flights operating around the world every day, right? And in general, air travel is at least 10 times safer than driving. Um, and in general, even if there's a small aircraft or a big aircraft, every crash or every failure that occurs will impact lives. It'll impact the industry. It'll impact the industries that rely uh, on aircrafts, and it'll affect public trust, right? So in general, like you guys said, safety is built into the system. There's redundancies, there's maintenance schedules, training, simulations, oversight committees. So things like these keep aircraft or flying safe, right? So even if I did a little bit of research, I pulled up some stats earlier to see that over the years, right, the number of crashes that happen in a year has decreased. The number of fatalities that happened over the past few years has decreased. I only pulled up stats for the past 20-ish years. So all of these have decreased considerably. And even the number of people flying has increased. Even though the number of people flying has increased, we're seeing less crashes, less fatalities. Sure, there's the 1 or 2 years of anomalies, but in general, the trend itself is decreasing. Um, so the thing is, from a financial perspective, safety has a cost associated with it. You need to invest some money to hire people to do the safety checks, to to follow the procedures. Um, you'll probably need to do tool calibrations, things like that, where you have other procedures to follow, and all of this costs money. But if you look at it from another perspective, if failure occurs, you'll have to pay a much higher cost, right? So first, you've lost the asset completely, right? Um, you you've you'll have to deal with things like lawsuits. The planes won't fly on time anymore because you need to clean up what has happened. Your brand has lost its image. People have less. They have less trust in your brand. They'll start taking other your competitors. Basically, they'll use their flights, right? So there's a lot of downsides to not investing in safety first, right? And if you are able to build and design a good aircraft using safety as your baseline, you don't need to worry much about like aftermarket issues or maintenance issues, insurance premiums, things like that will cut down on your costs later, right? Um, So, along with that, it also enhances the life of the asset itself. Like you have a flight that is built in with safety, it can fly longer than 15 years. Maybe it can fly for 20, 30, 40 years, right? With very minimal maintenance. Um, these are some of the things that um, companies need to keep in mind. And basically, if you can streamline your certification with built-in compliance. Like if you're able to every step of the way, you're complying with all the safety requirements. You won't need to worry about going back and redesigning your prototypes. Right? You have
If I
something to
can
say?
step in, yeah, if I could
Yeah,
step
go
in and
ahead.
say this, that since certification is my bread and butter,
Yeah, I know.
this is
That's
this
why I brought
is
it up.
this is where it actually triggers me a lot, and that's why I wanted to step in and cut you off over here. Um, this is the biggest problem right now that's happening in aviation world is the financial side not having the foresight, not having the long term vision to understand what are the implications of cutting budgets short and just doing the minimum required certification work so that they can resume their sales, they can resume their operations, but then worry about the problem that could come up 5 years down the line because of the subpar work that's been done to achieve the minimum to get the certification. And I guess this is where also the anomalies that you talk about in the last 2 to 3 years or the 5 years with the Boeing 77 Max issues and the other things that have happened, and also the countless number of near misses that have happened actually in different airports around the world, not just India, by the way. People like to harp on that, but around the world, it's all due to those short-sighted decision makings from the financial side to not adhere to robust decisions or the robust design goals to be met. Because again, I do sympathize with the business. The business needs to sustain itself so that we have innovations that could be done later on. But at the same time, playing whack a mole with issues that may come out later on, which you did not foresee because you don't want to foresee from a financial standpoint, will come back and haunt you, and you have to put multiple bandages to it. So, yeah.
Exactly. So that's what I'm saying. E- from the financial point of view, investing a little extra right now to make sure all those factors are built in makes for a long-term gain, right?
Mhm,
You won't see a loss or a dip later. You'll see the dip right now,
mhm.
but over a long term, you won't see like a loss of any kind.
Yeah. I guess this is where I think also it is a fault of the engineers as well. I guess we have been always in the realm of showing great design goals, showing robust designs, and showing and making and achieving systems that actually are, fail safe and efficient. But what we fail to do is explain to the product owners or to the value stream managers the long term effects of things that are missed while the designs were made, like explaining to them why making a robust design actually saves money long term. Because as somebody who is in the financial side, or as somebody who has to interact with the financial people as well, in my current job, I kind of sympathize with them on where they are coming from to cut budgets and only meet the minimum requirements of certifications. But at the same time, if it could be explained to them correctly and use techniques correctly, I think that is where the secret sauce lies to actually have a sustainable business.
Here, I have something to say here.
Okay.
On the finance guy's point of view, right?
Mhm,
Engineers have a track record, me being an engineer too,
mhm.
of over engineering stuff, right?
Absolutely.
We put crazy factors of safety for things that don't require that much. And the finance guys know, but they don't know enough. So they think you're over designing too much and want to cut your budget. So you need someone in the middle to take both sides,
to
right?
be honest, that is what the systems engineer's job is. A good systems engineer would understand the enterprise side of things and would actually come in and write the right requirements to show the business guys as well as the engineering side that here's where the balance lies. Like, yes, we need to have a
Exactly.
robust flight control system, but no, we don't need a robust satcom system. Like, we can have a an operating satcom system, but a robust flight control system to manage the budgets on an aircraft, basically. So that is something a good systems engineering team would write the requirements for and be the mediator in between.
Yep. And to get back to financial perspective, right? Some of the possible avenues or um, directions you can take safety technologies, right? One is you can use, like right now AI is very popular, so we can use predictive analysis or predictive maintenance schedules using AI. They can see when something might fail and say, okay, hey, don't run this engine yet, do maintenance first. And then we have simulation methods, right? We can do the designing theoretically, run multiple simulations, multiple failure analysis, and then start building. So that's a way you can save money before spending money to create prototypes, right? And to circle back to the AI thing, you need real-time data for that, right? So another way to do that is to monitor flight data constantly. I know, Sri, you had mentioned something about real-time flight data monitoring, right?
Yeah, it's called the Aircraft Health and Trend Monitoring System. So that is for the FADEC data. So as soon as an aircraft comes near an airport, it latches on to the airport's uh, wireless internet system and dumps the whole engine data onto the servers of like the operator. And the operator can then have a trend monitoring algorithm run to it to see, okay, the performance of this aircraft on this flight leg was not optimal, and I think there is a trend over here that it could actually need a repair soon, or this could be fine tuned, this engine could be fine tuned to have better performance and better efficiency. So things like that, there's multitude of algorithms that get run through that data. So that's the aircraft health and trend monitoring system from GE right now, but there's other OEMs also doing that. So yeah.
I think it's about creating a digital twin using IoT, which is Internet of Things,
Yeah.
where you simultaneously run the exact thing in simulation, what your actual product is doing in real life, and then you're able to simulate when breakdown would happen before the actual breakdown happens, so that you can push upgrades, you can do operational maintenance and maintain safety before an incident occurs.
And so, last few points I have is some of the ideas I have for, like, say, aircraft company or manufacturing company can integrate into their, uh, like, to show stakeholders, leadership, how safety can help is to sort of, every company now has its own dashboards, Power BI, uh, Tableau, whatever. So integrate into those the effects of the safety measures that we've taken, right? So if you've done like RCCA or um, failure mode analysis, or if you've done any sort of, if you have any data to how much the safety measures have helped in mitigating failures, you can integrate that into executive dashboards and say, hey, we've saved this much money by not having these failures happen, right? And at the same time, you can proactively, management can take steps to say, okay, this safety initiative costs too much. We're going to cut the budget for this. Give a budget value and say, okay, can you guys innovate something? Can you give us innovative ideas to have this amount of safety, but make it a little cheaper, right? And provide incentives for that, right? I'm sure employees will be more willing to think of new ideas and things like that if you're going to give them an incentive and say, okay, see, we need to adhere to this much safety, but it's supposed to cost less, right? A lot that's the crux of innovation, right?
Yeah, I guess that's where.
And
Yeah, go
yeah,
ahead,
go
sorry.
ahead. No, go ahead, go ahead.
No, I guess that's where I think the conversation or the battle is lost in some ways, where the management is not seeing the real picture, or the real picture is not getting
Exactly.
conveyed because of these tools not being used, especially Gen AI and stuff like that. I think those things need to be heavily utilized at this point, because the management will never be interested in investing into safety unless and until a path forward for recovery is shown to them. So basic safety is what regulations anyways dictate, but I think there could be more fail-safe systems being built and innovations can be done if the right narrative could be shown to the management, I guess. So
Exactly.
yeah.
And even the right incentives to be provided, right? No one's going to innovate for free. So just as a closing statement, I have, um, aviation safety is not just one person's duty, right? The industry needs to take into account safety. The passengers need to take into account safety. The regulatory bodies need to take safety into account. Leadership, companies, employees, everyone needs to contribute, right? To make aircraft, uh, flight, everything, uh, overall safe experience, right?
Mhm.
And having safety first culture, it protects people, it helps, it protects lives, livelihoods, um, and continuous improvement always makes it better, right? So, yeah, that's all I had to say.
I think we have to actually go into a deep dive of those aspects as well. Continuous improvement, the EHS side of things, the operational safety side of things. That actually has a big impact on the business side and also the financial side of any enterprise that's actually within aerospace. There are a lot of layoffs and budget cuts that have happened only due to on-floor safeties not being met or undermined, and then next thing you know, there is a whole production floor shut down for a month because of an incident, and that also causes a lot of issues. So
Loss.
yeah, uh, continuous improvements is a very big initiative that every company or every business has to take in aviation as well. So yeah, all right,
I guess that's what I had.
cool.
Are we done for today?
Ashwini, do you have anything else to add
Any
on to
final closing
the
thoughts?
to the summary episode of our aviation safety side?
Yeah, I would just like to summarize by saying that in general, aviation and aerospace safety is not a priority, it is the foundation.
Exactly.
We essentially are operating in environments where mistakes are unforgiving, and we are tens of thousands of feet up in the air, and usually we are flying over densely populated areas. So there is no margin for error, and every aircraft, every drone, it has people depending on it, whether they are passengers, whether they are operators, or whether they are people on ground. Safety is protecting all of these people. And because the systems that we're using are complex and high risk, uh, it is very important that we are protecting these systems from the smallest modes of failures, because these smallest modes of failures can often lead to large scale consequences. And we all know that failure is inevitable for any component. But failure is inevitable. Disaster should not be inevitable. Disaster should be something that can be avoided and should be avoided so that there is no catastrophe. And ultimately, like Parvesh said, trust is everything. The public's confidence in flying, the public's confidence in unmanned systems, it is all only because there is a safety record. And if the safety record does not exist, the trust of the people does not exist. And then the entire industry does not exist. So, any major failure can set back such an industry. So, it is very important to have a foundation in safety. And ultimately, like Parvesh said, safety is what drives innovation. We have always learned from our mistakes whenever such incidents have happened. That is what has pushed the next wave of innovation to make travel safer. So some of the most advanced technologies in aerospace, such as fly-by-wire, such as collision avoidance systems, these have all been developed in the pursuit of safety. So that is why at the end of the day, uh, it is not just about rules and checklists. This is not about just ticking a box. It is about designing systems that protect people. It protects trust. It adapts to the unexpected, and it earns us that record that this is technology that can be trusted and that should fly.
Got it. All right. I think we have spoken a lot about aviation safety. At the surface, though, there's a lot of deep diving that we have to do in our future episodes. And I hope you guys like this episode. Please like, share, and subscribe to our channel. All your comments, we take them very seriously. Please do also reach out to us on. Uh, uh, yeah, please do comment. Yeah. Please do also reach out to us to ground control to major nerds at gmail.com. Um, we we are actively looking at all your feedbacks that you are giving us. We are really loving the support that we are getting, and yeah, please also do comment and let us know which topics do you want to actually deep dive into in terms of the aviation safety. If some of the topics resonate with you, please do put it down in the comments, and we will make sure that we prioritize those topics. But yeah, going forward, I think we will do a series of aviation safety episodes, and also we will look into the incident that has happened on June 12th and make sure that once the investigation is completed, we will give our complete detailed understanding of it as much as we can.
We can even probably pull up the report and go through it step by step, page by page.
Yep, exactly. So we'll do that for sure. All right. Thanks a lot, guys. Thank you for tuning in. See you in the next episode.